Speaker for this online event is Dr. Sophie Spirkl. Dr. Spirkl earned her PhD at Princeton in 2018, under Maria Chudnovsky and Paul Seymour. So she's carrying forward the heroic program of this century's modern graph theory. But she's also, some of her papers deal with computational complexity, and there's even one on called about a matroid look at coding of graphs, entitled Entropic Matroid. So I welcome Dr. Sophie Spirkl. So she's currently at a postdoc at Princeton and will be moving on to Waterloo pretty soon.
Okay, so thanks everyone for coming, even though I'm welcoming you to your own home probably. But please feel free to ask questions at any time, either via chat or via audio. I'm happy to answer questions and make this talk, interactive. And if I don't get through everything in my slides, then it probably went well for everyone. And thanks so much to the organizers for organizing all of this in Albany and then also online. It's really great to be here, if only virtually. And also, thank you for the introduction. I think that's the best pronunciation of my name by anyone who's ever introduced me. So that was very nice. So my talk is about excluding an induced subgraph from a sparse graph. But since then, we've come up with a shorter, more catchy title for the same topic, which is pure pairs. And this is based on joint work with Maria Chudnovsky, Jacob Fox, Alex Scott, and Paul Seymour. And I'm going to start, but please interrupt me at any time. And let me bring up the chat so I can see that also. So this talk is about graphs, as you probably already suspected, and it's about induced subgraphs. Everything is always about induced subgraphs, at least for me. And so if we have a graph, an induced subgraph is something you get to by just deleting vertices, which is different from other containment relations because you're not allowed to delete edges unless you delete them because you deleted the vertex that's one of its endpoints. And you're not allowed to contract edges or anything like that. So if we have a graph that's just a 5-cycle, which is here on the right, then this graph H, the green graph, is an induced subgraph because we just deleted this top vertex, but these other two graphs aren't, because to make J, we would have to also delete an edge, and to make K, we would have to contract an edge. But so this is a very restrictive containment relation, which means it's very hard to say if I exclude something as an induced subgraph, what happens. Certainly if we exclude some small graphs, G as an induced subgraph, we can say what happens. Like if I exclude just an edge, things get very easy. But as soon as your graphs are a little bit complicated, like this graph G, the 5-cycle, if we exclude that as an induced subgraph, we can't say very much structurally. And so the goal of this talk and the goal of pure pairs is in part to say, what is something big picture I could say about a graph if I exclude something as an induced subgraph that doesn't just work for small induced subgraphs, but works somehow generally. What generally changes in a graph upon excluding just anything as an induced subgraph? And so the kind of thing I want to talk about are pure pairs, which means I'm looking for subsets of the vertex set. And I don't care what happens within the subsets, I care what happens between. So if here I have two subsets of the vertex set, then I'll call them complete if between them all edges are in, and again, I don't care what happens within them. And I call them anti-complete if there are no edges between them, and this is the kind of thing we want to happen. Just sort of because if you want to make a graph that doesn't have very many different induced subgraphs, you could always go with put no edges in your graph or put all edges in your graph. So the hope is that there's some partial reverse where you say, if some induced subgraph doesn't occur, then there's some large-scale thing where we don't have edges, or where we do have all possible edges. And so I'll call A and B a pure pair if between them all or no edges are present, so if they're complete or anti-complete. And then for a class of graphs, I'll write there FG pure if A, one half of the pure pair, can be chosen to have size at least f of n, where n is the number of vertices, and B can be chosen if size at least g of n. So when this occurs during the talk, usually we'll say something like epsilon n pure to mean we can choose two linear size subsets of the vertex set. And between them all or no edges are present. Okay, so far? So this is the setup. And now you might ask, why are we doing this? And the original motivation for this is a long-standing conjecture about induced subgraphs that addresses what I said in the beginning. What is a general thing that happens when we exclude something as an induced subgraph? So we're going to say that a class of graphs has the Endochinal property if there's a positive constant delta and every graph in my class has a clique or stable set of size at least n to the delta, which means my class of graphs has the Endochinal property if for every graph in my class, I can find a fractional polynomial size subset of the graph, and here I either have no edges or all edges. Right, a clique means there are all edges within that subset, and a stable set means no edges within that subset. So this is different from pure pairs because this is asking, instead of what happens between the sets, it's just one set, and we want within the set the same thing to always happen, either all edges or all non-edges. And so the conjecture that motivated all of this is the Endochinal conjecture, a long-standing and hard and well-known conjecture about induced subgraphs, which says whichever graph we exclude as an induced subgraph, the class of H-free graphs has the Endochinal property, which is a beautiful conjecture, but unfortunately very hard. So we know it for some simple graphs H. And I made you a list of some of the things we know already, but the graph we saw in the introduction, the 5 cycle, is one of the graphs H for which we already don't know. So while we know it for some graphs, and in fact an infinite list of graphs, there's open cases as small as this one for which we don't know if it's true or not. But the good news, or what we thought was the good news at the time, is that if we can always find linear size pure pairs, that's enough to say a class has the Endochinal property. So there is a way to turn linear size pure pairs into polynomial size cliques or stable sets. And that's, a fairly easy inductive argument. So if only we could show that every class of graphs that excludes some induced subgraph was epsilon n pure, we would have proved the Endochinal conjecture. But of course, it's not that easy. So, in fact, this won't solve the Endochinal conjecture at all. You can prove that if H-free graphs have linear size pure pairs for some graph H, then H is an induced subgraph of a three-edged path, this thing. But also the other way around. If you exclude this thing or any induced subgraph of it, you get linear size pure pairs. And the reason it is this little graph is because this is the largest graph, such that this graph and its complement, which is this graph, are both forests. And every graph such that it and its complement are forests is an induced subgraph of this little 3-edge path. So we can see that the 3-edge path works for endochinal, more easily. Because in fact, when you exclude it, you get perfect graphs, and in perfect graphs, you always have a clique or stable set of size root n. So in some sense, this is where I could stop and say, clearly pure pairs are not the way to attack endochinal. Right, if we wanted to prove the full conjecture using this strategy, this tells us we can't. And in fact, the only case we can prove with this strategy, we can prove much more easily without it. But so this restriction due to Liebenau and Pilipchuk is saying we need to exclude a forest and the complement of a forest. So maybe we can make some progress here. And so the first goal is to say, maybe we should exclude H and its complement, and we can get closer that way. But right, so if the question is just which graphs H give us linear sized pure pairs, here's the answer. We've answered that question. It just turns out the answer isn't that helpful. So let's try to exclude a graph and its complement. And in order to go in that direction, we're going to use a nice theorem of Rödel, which says we can basically restrict our attention to sparse graphs. So let me say what we're doing more slowly. Let's call the graph epsilon sparse if for every vertex, that vertex and its neighbors is at most an epsilon fraction of the whole vertex set. The reason we count the vertex itself is just because this tells us that epsilon sparse graphs are also, kind of big. They have at least 1 over epsilon vertices. And then there's a theorem of Rödel that goes kind of in the right direction, because it says if we exclude any graph as an induced subgraph, then any big graph that doesn't have our small induced subgraph has a linear size set that, while it doesn't have no edges or all edges, at least it's either dense or sparse. So it's saying if we have a target sparsity epsilon, then if we look at a big graph G, which is H free, there is some linear size fraction J of size at least delta times the number of vertices in G. And additionally in J, either J itself is epsilon sparse or its complement is. Or it could be that G is just small. But we can ignore that because sort of small graphs don't make a difference here. We can always deal with them separately. So this, you prove this using the regularity lemma, for example. I mean, it's basically saying, well, if your graph is, not very sparse anywhere, not very dense anywhere, then you can embed every graph H you want as an induced subgraph. But if that's not true, then there's a reason it's not true, which is that at some point you try to embed H and you get to a bit that's too dense or too sparse to proceed. And so we'll use this extensively because from now on we can focus just on epsilon sparse graphs, right? This is telling us whenever we exclude some graph as an induced subgraph, there's a bit that's sparse or its complement is sparse. So we either work in that graph or we work in its complement, but from now on it's fine to assume everything is epsilon sparse. And that helps. So the way it helps is, well, first of all, we can now embed things more easily and we can use sparsity to say, when we pick a vertex, its neighbors are kind of irrelevant in the graph. They're just a small set. but also it breaks some of the counterexamples that show that we need to exclude a forest and its complement. Because if we're in the sparse case, it's actually enough to exclude just a forest. And so we actually have an answer here too for when can you get to linear size sets with all or no edges between them, which is you need to exclude a forest if you're in a sparse graph, which implies that if you have a forest F, then if you exclude F and its complement, then you get a class of graphs that satisfies the Endochinal conjecture, which is, not what we wanted. We just wanted to exclude one graph. But even that, isn't something we know yet. We don't know if the Endochinal conjecture holds if we replace exclude H by exclude H and its complement. But so this theorem and the theorem of Leibniz and Polipchuk that says even in a sparse graph we have to exclude a forest tell us that for epsilon n and epsilon n we've answered the question completely. So what I want to do in this talk is basically look at what else we can say. How can we at least get sort of close to linear and linear? Or what happens if we exclude more than one graph? This is the answer. We know what works for forests, and now the goal is what else can we make work? How can we even get close to this? So the first thing to look at is what happens if we exclude something that has cycles but more than one graph. The way the Leibniz and Polipchuk counterexample works is it's just a graph that doesn't have a linear size pure pair but also doesn't have short cycles, which means that whenever we exclude something and want to get linear size pure pairs, we have to exclude either a forest or graphs with arbitrarily large girth. So definitely we can't use an infinite family excluded if, each of them has a short cycle in them. So can we do the opposite? If we look at a family of graphs and somehow its girth goes to infinity, does that work? And here's a way in which that works. One way to make a family of graphs with infinite girth is to say, let's look at our favorite graph H. And not just exclude H as an induced subgraph, but in fact, exclude all its subdivisions, which are just graphs you get from putting vertices in the middle of edges, replacing an edge by a path. If we exclude H and all its subdivisions, then we've excluded a family of graphs with infinite girth. And this works. If we exclude that, meaning H and all its subdivisions from a sparse graph, we still get two linear size pairs with all or no edges between them. In fact, in the sparse case, we always get no edges. But if you look at the graph H over here, you'll notice that in order to make a subdivision have infinite girth, and as we keep adding vertices, it's enough to put subdivisions on some of the edges. In fact, you could pick out your favorite tree in the graph and say those don't get subdivided, everything else does. And still, if you exclude all the subdivisions that only subdivide the edges not in your tree, you would have graphs of arbitrarily large girth. So this could work. And we didn't prove that, but we did prove that you can pick your favorite path and say, I'm only going to do subdivisions that don't subdivide my favorite path. But so for more than one graph, this is somewhat close to the best we can do. And so before we continue, I want to show you the construction, the reason why we can't do better, and the counterexample that tells us what we do need to exclude in order to make things work. So the first construction, the one that tells us let's exclude a forest, is we can just take a random graph with very low edge density, every vertex just having large constant degree in expectation. This, as it turns out, already with high probability gives you a graph that doesn't have two linear size sets with all or no edges between them. And also, it doesn't have many short cycles. In fact, it has barely any. So we can just delete the vertex sets of short cycles. And this by itself tells us if we just exclude one thing, it better not have a cycle, because we can get rid of all cycles that are up to the size of H, for example, and then certainly if H has a cycle, we won't get it as an induced subgraph. And this is not very tight, right? You'll notice that in order to get this, we don't have two linear size sets with no edges between them. We just needed to give every vertex basically constant degree, which is an extremely sparse random graph. And then we deleted short cycles, but in fact, in order to be able to delete short cycles, we could have had somewhat higher edge density, right? The expected number of short cycles with this edge density is tiny. We could have, in fact, given vertices small polynomial degree, and still we would have been able to delete cycles. So let's do it a bit more carefully. Let's instead increase the density, right? So we're going to put a random graph and now let the edge density be n to the minus delta for some small delta. The outcome is still likely to be epsilon sparse, because in order to not be epsilon sparse, you need a vertex of linear degree, and that's certainly not going to happen unless p is a constant. I should say, almost certainly not going to happen. So with high probability, this is still going to be epsilon sparse. But because we increase the edge density in order to make degrees not just constant, but bigger, we're very likely not going to find a pure pair, even if instead of linear size, we ask for n to the epsilon, where n is less than 1, where epsilon is less than 1, n is not less than 1. And still, if H is reasonably dense, where even a short cycle counts as reasonably dense, we expect to get at most a linear number, a small linear number of copies of H, and so with high probability, we can still remove them all. So this construction where we increase the edge density until we could just still remove all copies of H tells us for a graph H, what is the upper bound? What size of pure pair could we possibly still hope for? And it shows you that if we just exclude one graph H, then the size of the pure pair we can still hope for depends on the sort of densest induced subgraph of H. But in particular, if you have a cycle of length k, then you shouldn't hope for epsilon n. In fact, you should hope for something that's at most epsilon n to the k minus 1 over k for the size of your pure pair. So this is telling us a trade-off between how dense is the graph that we exclude and how big could pure pairs possibly still be. It tells us certainly that if we exclude anything that has a cycle, we won't get linear, but it tells us a little more. And now we can try to look at a graph H and match this bound, which generally won't be true. But maybe we can match up to a constant, maybe we can exclude something where this density is very, very close to 1 and hope that we get pure pairs that are not linear, but very, very close to linear. But before I continue, I should say this is also not yet the answer to everything. Right, we now have a construction that says we should exclude things with large girth in order to get pure pairs, but that's not enough either. For example, Jacob Fox gave an example of a class of epsilon sparse graphs that are not epsilon n pure. They're comparability graphs, which means they're perfect. So if we exclude odd holes, which is certainly an infinite family with girth going towards infinity and unbounded, then that's not enough to get linear size pure pairs. And also, we can throw in odd antiholes for free and still we won't get linear size pure pairs. So sort of, there's still a gap of, we can't guarantee something of fixed parity. So we know that if we exclude a graph H in all its subdivisions, then this works, we get linear size pure pairs, but this result of Fox tells us it's very unlikely that we can prescribe some amount of parity or residue for the length of the subdivision of the graphs we exclude. So this kind of suggests that excluding all subdivisions might be the best we can do, or at least if it's not as easy as we need unbounded girth, but we need some amount of, we exclude more than just odd girth things. So I'll proceed instead with looking at graphs where we no longer want to get linear size pure pairs, but we want to get something smaller. And again, the construction tells us that if the graph is dense, then we can't hope for it to have a very large pure pair, but if it's sparse, we might. So the first thing that we saw is, well, we can show that for some graphs, we might need to go to n to the epsilon for some epsilon less than 1. But this theorem of Endochinal and Pach tells us that, we've scaled down our ambitions enough. Now we've gone to something that actually works, which is if we exclude any graph H, then we do get a pure pair with both sides of size n to the epsilon for some positive epsilon. So we wanted linear. We know that linear generally won't work, but in general, we'll have to look at n to the epsilon for some constant epsilon less than 1. But then it does work, there is such a constant, and in fact, this was used to prove an approximate version of the Endochinal conjecture, where we show that, well, not we, but Endochinal and Pach showed that while we don't know how to get a clique or stable set of size n to the delta, we do get something of size to the delta square root log n, which is nice because while it doesn't prove the conjecture, it does distinguish H-free graphs from general graphs. Right, in the class of all graphs, you can generally hope to find a clique or stable set of that size, but if you exclude some induced subgraph H, you do get something of that size, which tells you that, the Endochinal conjecture is at least going in the right direction. If you exclude some graph H as an induced subgraph, you do have larger cliques or stable sets than usual. There's something going on with cliques or stable sets, even though we can't necessarily find them of size n to the delta. And I'm going to show you this proof because it's nice and simple. So this proof relies on just embedding the graph H. So we have our graph H, and say we have vertices V1, V2, up through Vk, size of the graph H. And we want to find H as an induced subgraph in some big graph G. Let's split up the vertices of G into sets of size n over k. So here are k sets of size n over k. And you might have to round down, but rounding errors don't make a huge difference here, because if the graph is small, you just say, take a non-edge or take an edge, and here's a reasonably big pure pair if your graph G is actually very small. So let's not worry about rounding, but here are k sets, and here's the graph H, and we have some edges and some non-edges. Let's embed the graph H into these sets, embedding one vertex of H into each of the boxes below. In order to do that, we want to pick some vertex who's going to be V1, but we know that V1 has to be adjacent to V2 and non-adjacent to V3, and has other adjacencies to other vertices. So if we settle on this vertex as being V1, there's a goal to say we don't want to mess up the rest of the graph too much. We want to have a good number of options still for each of the other vertices. So I can look at a vertex here and look at how many neighbors does it have here where I'm supposed to have neighbors, and how many non-neighbors do I have in box 3 where I'm supposed to have non-neighbors. Right, I can look at each of the boxes for this vertex that I want to be V1. And if each of them has size n to the 1 minus epsilon over k, each of these sets of vertices that could still be V2, could still be V3, could still be V4, and so on. If each of those sets loses as a factor of at most n to the epsilon, then I'll say that's a great choice for V1. I'm going to stick with that. And I'm just going to keep the sets of vertices that can still be V2, can still be V3, can still be V4, and so on and so forth. And so now what I've done is I've gone from sets of size n to the k to making them smaller by a factor of n to the epsilon. But I embedded the first vertex, and if I embed all the other vertices in their right boxes, I will make the graph H. So if this succeeds, if I can find a good V1, I can now proceed by induction, right? Look at choices for V2, see which of them have neighbors where I want them to have neighbors, and have a good number of neighbors where I want them to have neighbors, and a good number of non-neighbors where I want them to have non-neighbors, and so on and so forth. Right, as long as we can get each vertex that we fix, each vertex of G that we choose to be a certain vertex of H in such a way that the number of vertices that can still be the vertices of H we haven't embedded, as long as the number of candidates for each remaining vertex of H remains large, goes down by a factor of at most n to the epsilon in each step, we're happy, because then if you choose epsilon to be less than 1 over k, that means that when you're choosing Vk, there's still a candidate left over, which is all you want. So if in each step we can pick our vertex to have lots of neighbors where you're supposed to have neighbors, and lots of non-neighbors where you're supposed to have non-neighbors, as long as we can always pick a vertex that doesn't reduce the number of candidates too much, we're going to be able to find H. So the only part that might not work is what happens if we looked all through this first box and nobody looks like a suitable vertex V1. Right, we looked at all of this box, and each of them was faulty in some way, either by having not enough neighbors where you're supposed to have neighbors, or not enough non-neighbors where you're supposed to have non-neighbors. But we only have k boxes, which means that a large fraction of the vertices in this first box were unacceptable to us for the same reason. For example, maybe these were all unacceptable because of box 2, meaning none of them had enough neighbors in box 2. And so now we're going to find a pure pair. And the way to find a pure pair in this case is just saying these guys in this circle on top were all unacceptable because of box 2, which means each of them had less than n to the 1 minus epsilon over k neighbors in box 2. But right now, box 2 has size n, and in general, we only want an n to the epsilon fraction, n to the minus epsilon fraction of each of the boxes. So I can just greedily pick vertices in this box on top. And let me pick out n to the epsilon. Let's say n to the epsilon over k to be safe. Then none of them have any neighbors in the next box. And in fact, if I look at all of their neighbors together in this next box, that's still not a very large fraction of the box. So I'll take my set here that I just picked greedily, and I'll take what's left over here where none of them has neighbors, and I get a big pure pair. Right, so more generally, if we have vertices and their degree is actually that low, it's not linear, but actually n to the 1 minus something, we can always find a pure pair by just taking a bunch of them and saying, even taken together, they don't have enough neighbors to take up most of the graph. So I can just look at their joint non-neighbors, and that's still big. So you get a big pure pair. So this proves the theorem. Let's say it again very briefly. So what you do is you say, I have these boxes, that's where I plan to embed H. And at every step, I look at a new vertex of H and say, I'm going to pick a vertex in this box now that's going to be that guy. Only making sure that you still leave yourself plenty of choices for the remaining vertices of H you want to embed. And in order to make sure that you still have plenty of choices for the remaining candidates, you need to have lots of neighbors and non-neighbors in the appropriate boxes. But if you don't, then you have a big subset of a box that either doesn't have very many neighbors or doesn't have very many non-neighbors in one of the other boxes, so you can just greedily pick out a pure pair. Which is kind of a nice proof. I mean, there's some carefulness going on with the exponents, but it's a nice proof. And in fact, we didn't just prove you can find H. We picked in the beginning these boxes in G and found H in those boxes. So if you put an order on the vertices of G and said you wanted to find H, but also find H in some certain order that matches the order of vertices in G, you could still do that. So this proof is very robust and actually works even if we order the graphs, which might matter in a second. So we've seen so far, if we're just excluding a single graph, then we know exactly when we can get two linear sized pure pairs, and that's, we still know the answer if we restrict to sparse graphs. And we know that we can always get a pure pair with both sides of size n to the epsilon. So the natural question is, well, maybe sometimes we can get a compromise between the two. maybe we can get one side to be linear and the other side can stay small. And this is an open question that's very annoying because we can't even solve one of its, the first cases you should be able to solve. So the conjecture is that actually for every graph H, if you exclude it, you get a pure pair where one of the sets is linear and the other has size n to the epsilon. Which would be quite nice and would probably give rise to proof methods that would let us prove a closer approximation for the Endochinal conjecture. But we don't know. Here's what we can prove. We can prove it for the sparse setting for almost bipartite graphs, which means graphs that you can partition into sets A and B, and one of them doesn't have edges, and on the other side you have maximum degree 1, and between them you can have any edges you want, except you're not allowed to make a triangle. So almost bipartite graphs in some sense are still very sparse graphs. And they can be fairly dense, but sort of you still have A and B, which are basically stable sets, so they're behaving in a way that's close to bipartite graphs. But while we have all these complicated graphs, which if you think about it for a second, these graphs include all subdivisions where you subdivide an edge at least once of any graph, and they include C5, which was and is sort of the hard annoying case where Endochinal is still open and we don't know what to do. So these include lots and lots of graphs, but they don't include triangles. And that's sort of where we're stuck on this. So if you would like to do me a favor, please solve this case. This is one of the open problems that I've brought to many places and nobody has solved it yet. So please email me. I will appreciate it. In fact, we can't even prove that if you replace this by something reasonably small. Okay, be unambitious. Prove this. Make it size log n. I'm not picky. You can Google my name for my email address. So this is where we're stuck. If we're just looking at graphs and excluding something, we know that both sides n to the epsilon is always true, both sides linear is almost never true, but we know exactly when it's true, and this compromise between both should always be true, but we really don't know how to do it, even for a triangle, which is a case for which we know Endochinal. Right, I mean, for a triangle we can prove Endochinal because it follows from Ramsey, or just by saying, well, let's pick a bunch of vertices. And, either we can pick a big stable set or some vertex has big degree, but if it's got big degree, then its neighbors are stable sets, so here's a big stable set, right? Triangles in the Endochinal world are the opposite of a challenge, so please solve this. But since we can't solve it, we have to do something else. And the something else is, if you think back to the construction, we actually had a more differentiated bound other than linear or less than linear, but we had a bound that depended on the density of H in a way where, I'm making things yellow, sorry, that's not on purpose, where the density was denoted by this quotient, and so this quotient tells us something about the girth, but in fact it tells us a little bit something different. In fact, let's look at a graph H. We've already seen that if we exclude all subdivisions of H, then we're good. We can get linear size anti-complete pairs. So what if instead you say, I'm going to make the girth of this huge and the density low by subdividing each edge 1,000 times? And so you can. And we know that that still has cycles of length, something times 1,000 if h had a cycle to begin with, so you won't get linear size pure pairs. But now the construction tells us that this bound, the amount we're away from linear is very small. Said more carefully, now we should be able to get pure pairs where maybe we don't write linear on each side, but we write n to the 1 minus delta, where delta is very tiny, because we subdivided it lots of times, and so the construction is not very strong. It has to work a lot to get rid of those really long cycles, so it does admit big, if not linear, pure pairs of size, n to the something that's close to 1. So can we match this? And we can, in the sense that if you give me your favorite positive delta, then I can tell you, here's a k, and if you take your favorite graph, well, you should also tell me your favorite graph h in advance. Here's a k, and if you k subdivide, put k points in the interior of every edge of graph h and exclude that thing instead of h as an induced subgraph from an epsilon sparse graph where I also get to decide on epsilon, then you have a pure pair, and in fact, we can get one of the sides to be linear. And the other, we can't get it to be linear, but you got to pick delta. You got to pick how close it was to 1. So in some way we can match the construction. At least for now, the first way in which we match it is that it tells us that how close we can get to 1 is related to the girth of a graph. But if you tell me how close you want the pure pair to be to n to the 1, I can tell you how big the girth, the number of subdivisions should be in order to make that happen. But in fact, we can do this more carefully. And in order to do this more carefully, we need to look at what the actual bound is that the construction gives us. And it turns out that the bound is related not to subdividing everything, but to, you get to fix a tree and subdivide everything else, which we already saw for how do you guarantee to make the girth large, right? You don't actually need to subdivide everything. You just need to subdivide everything a bunch, except your favorite tree can stay unsubdivided. And so even for those things, we can prove that you get close to a linear size pure pair. And so we're sort of matching the construction here. The construction, what parameter of a graph has to be close to 1 in order to get a close to linear size pure pair, and we can prove that if you make that parameter close to 1, then you do get a big pure pair, and in fact one side is linear, which is nice. And probably an artifact of the fact that these things definitely won't have triangles. So for graphs, we're kind of really close to saying exactly what you can and can't get in this realm. We know when you can get linear, and we know when you can get close to linear, and there's that awkward case of the triangle, but at least we can get linear and polynomial sometimes. But for graphs, we have a fairly good grasp of some of the things you can and can't do. So one of the questions we can ask from there on out is, let's look at ordered graphs, right? It was kind of interesting to see this proof of edge channel path play out, and we could actually embed a graph H in the bigger graph G, not just in any way, but in our given favored order. So maybe that's always true. Maybe we can say all these previous theorems again, but add the word ordered wherever appropriate. And part of the reason we care about this is that the Endochinal conjecture remains the same. In that if we can prove it in all graphs, or if we can prove it in ordered graphs, it follows for the other class. So maybe ordered graphs are what we should be looking at. And there's also a question about tournaments, but let me skip that. And so for ordered graphs, you can modify the construction because you can now remove things and somehow remove things in order without creating infinite loops, which allows you to exclude even more things. I'm going to not tell you the details of the construction, but in ordered graphs, everything gets even worse, right? For normal graphs, we said it's only the 3-edged path, and then we said maybe we should make it sparse, and then it became porous. In ordered graphs, even if you're looking at H-free epsilon sparse ordered graphs, in order to get linear size pure pairs, your graph H should, well, it still shouldn't have a cycle. Now it also shouldn't have a 2-edged path going forward, and it shouldn't have a claw, and it shouldn't have any of these 3-edged paths in these orders. So what's happening with ordered graphs? In order to get linear size pure pairs, if we're looking for excluding a connected graph H, we can do it for this one, which is not very impressive, but already is proved using a harder theorem. And we don't know about this one, and that's it. So in ordered graphs, it's even harder to get linear size pure pairs, and in fact, to the best of our knowledge, you can do it for this one 2-edged graph, and maybe you can do it for that one specific 3-edged graph, and then some graphs that have connected components, but it's really hard. So ordered graphs are even harder to find pure pairs in. We can't even get linear size pure pairs for all trees. But we saw from the Endochinal proof earlier that we can always get polynomial size pure pairs, right? That proof works just the same because we actually did an ordered proof. We never changed the order of anything. And so for trees, we can prove that you can get sort of close to linear. But we can't even remember from normal graphs we had that if we subdivide stuff enough, we can get one side to be linear, but in ordered graphs, even for ordered trees, we can't even get one side to be linear. So ordered graphs are hard. And here's another open question that I should have written, please solve this. So I'm running out of time, but let me first sum up. Hopefully I've convinced you that pure pairs are interesting, even though they're entirely, I shouldn't say entirely, but mostly not useful towards proving Endochinal, but they're a different and more tractable way of quantifying how excluding an induced subgraph makes there be large-scale structure in a graph. But there are some simple cases, the triangle and this 3-edged path in ordered graphs, that we still can't do. So this is still something that isn't all that old yet as a research area, and we still have some fun, interesting questions. Also, please solve them. But let me stop talking for now and show you all the slides that you didn't see. usually at conferences during the last plenary talk, I should say, we should all thank the organizers for organizing this conference. This time the poster talks are also plenary, but still, thank you so much for organizing this, putting it together online on such short notice. And thanks to everyone for coming. Please unmute yourself if you clap because I can't see everyone.
Okay, thank you. Thank you.
Thank you.